next up we have Zion Leonahe Basque, who's going to do, this is my favorite name, right? There's a lot of names, I mentioned this earlier, but I do really like his talk. This was a fan favorite amongst us at Vector 35, the Binary Ninja team. His work is really, really quality. If you haven't read like the research, the paper that kind of underpins a lot of this, you should definitely do that. But this is really one of those like, call outs, like let's call out the tooling, let's call out the industry and show that we can do better. And that's really what it's all about. So we're all excited to see him do that. Please welcome Zion on stage.
Testing. Test. Everybody good? Wow, that was a pretty epic introduction. So I think, let me get some timer good. Make sure we have the time. All right, let's get started. Thanks everybody for coming. It's a pleasure for me to be up here. There have been so many cool talks today. I'm just feeling honored to be on this stage. But before we get into the actual content, let's get into me. So who am I? Who is this guy that's trying to come up here and talk to you all about some decompiler nonsense, some things about compilers, something about optimizations, right? A whole bunch of topics. All right, so I'm Zion. I'm Zion Leonahe Basque. That was an epic pronunciation. That is my name. I'm also Mahalo's Online. You might know me as this pixel guy if you know me on Twitter. I am native Hawaiian, as the middle name might suggest. I am from the big island of Hawaii. Non-ironically, it is the biggest island in the chain. And I'm also from Shellfish. I'm from this hacking team. We do a lot of CTFing. We've been at DEF CON a long time. And we also just did some AICC stuff. We competed in a DARPA challenge. We got $2 million to be in the finals. We're competing in it in August, right? So come check us out. But kind of more relevantly, I'm a huge decompiler nerd. I write blog posts about this kind of stuff, year-end reviews about decompilers, some of the science behind it. I publish papers. I try to run this thing called the Decompilation Wiki. So to kind of summarize of all these topics, I'm just kind of a huge decompiler nerd. I like to use them a lot, so I do dog food. I do use my own decompiler, and it crashes all the time. But this is how we get better decompilers. And finally, I hate pineapple pizza, probably one of the most important points in this talk. I am native Hawaiian after all. Anyone who tells you they like pineapple pizza is a liar. So on to the actual goals of this talk, though. Why am I up here? Why am I yapping at you? I really have two possible goals, two alternate realities of this talk, depending on which one you want to choose. First possible reality, complete rebellion, anarchy. All right, we rebel against the decompiler developers, everybody who's made decompilers. We even rebel against the people who have funded decompilers because they're not good enough. That's one of the goals. You guys burn them down, exactly, in rebellion. Or, alternatively, if you're not into rebellion, looking to be a little more chill, you can also give our decompiler a shot. Yeah, I hope I can convince you of that by the end of this talk. So let's get into the talk, right? You guys are the reversers, right? You fight binaries all the time, to the death, gladiators of this kind of binary realm, right? And when you're fighting things to the death, you need good tools. One of those tools, as you guys are very well aware with, is disassembling things, right? Here in goes a binary, all these bytes, out comes some kind of instruction level stuff. It's got a graph. You're like, I love graphs. This is the exact tool I was looking for. Except it's not the exact tool you were looking for because it's a little too complex. So you're like, okay, get the next best thing, a good tool. You take that disassembly, you put it into your decompiler, and what comes out is linear code. And we love decompilers because they do that, right? They make these complex graphs into very linear, very understandable code. It's the best. All right, let's be real, right? That's not what the code actually looks like. It looks like this. It looks crazy, right? You can't even read it. I had to truncate it. This isn't even the full code. There's about 15 gotos in here. There's like broken if statements. Things are nested. Some of the code didn't even decompile correctly. This is just a mess, right? Decompilers are complex code generators, and that's really unfortunate, right? Because we like to read good code, but it's also a problem for security in general. Right, so let's even take some simple cases, right? You're saying, all right, Zion, you showed us a big graph, right? That's neat. Can you show me something simpler? Here's a 6-line program. Take this 6-line program, put it in GCC, you get your binary out, take any modern decompiler, any one of your choosing, maybe even secret ones I don't know about, and this is what you get at the end. That's actually fairly different, right? 6 lines became something around 10 to 11 lines, and that's kind of weird, right? Because what's going on here? There's a goto, by the way. There's a goto in the decompilation. There were no gotos in the source code. This is only 6 lines. I only wrote 6 lines of C. In addition to that, and this is the weirder one, there's 2 calls to puts 2. There's only 1 call to puts 2 in the source. So there's an extra call in my decompilation. And this is a simple case, right? This is 6 lines of C. You can go and compile this right now on GCC. So is decompilation really that broken, though, right? I show you some 6 lines. You're like, all right, he's yapping about 6 lines of code. He contrived the example. I've looked at malware before. I've looked at crazy stuff. And you know what? I say let's pull it back a little bit. Let's get a simple piece of code, but maybe a little bit more complex than 6 lines. Let's actually pull a piece of code that's real world and is likely running on all of your machines right now. Maybe not running, but it's at least present there. You may have used it before. We're picking a very simple program, your favorite program. It's called format. What does it do? It formats things. It formats strings specifically. You put in strings and it formats them. Maybe you haven't used it before. I have actually never used it before except for this exact demo I'm showing you. All right. It's pretty archaic. It's essentially like the lesser version of ChatGPT. You say, hey, man, make the lines like, 10 characters long, and that's what it does. And it's something important to remember about this. It's Unix. It's pretty simple. It changes text to meet specific formats, and it takes some flags to do different things with the text, because maybe you have different requirements. Fairly simple, 1,000 lines. Take note of the 1,000 lines. So let's look at just 10% of this program, just the main function. The main function in format, this is the source code. You don't really need to read it. You can just kind of vibe with the length. It's about 130 lines. It's fairly linear. There's a switch statement. There's linear code. There's assignments. Fairly fair. It's just kind of normal code. Let's take a more microscopic look at this main function. Right? I think a lot of us have written a main function before, hopefully everyone here, because you need to run your binaries. What main functions are usually doing is dispatching kind of things, right? You parse some arguments, you dispatch to all these calls you're going to do, whatever your real program does. Right, so this is it. This is the arg parser. Fairly simple, parses args, different characters. Except it's not simple, because when you compile it and then decompile it, it becomes this thing. Well, what is this? What am I looking at? Right? Let's look at this switch case. Except where's the switch case? The switch case is gone. There's no switch case here. I didn't truncate the switch case out. It's just gone. The switch case has turned into a series of nested if statements. I have also not shown you all the if statements here. There are more than are being shown. So there's this explosion of code. What happened? There's also some interesting things going on here. There's gotos. There were no gotos in this source code. Where are these gotos coming from? Additionally, that first one, goto label 53, that's kind of concerning. It looks like it's making a loop inside of this if statement. There's no loops in this. This wasn't in a loop. This is just a switch statement. It's linear. It gets executed once, unless you're looping on that. But right, this is not supposed to be looking like this. So you're saying, OK, Zion, we know switch cases are hard. I have seen a switch case before. It can be pretty complicated. And I agree with you. It can be pretty complicated. So let's look at just sanitizing some of the input you might have done. All right, so you put in this thing into your format thing. You're saying, hey, can you please shorten the lines? Can you please do all this stuff? And format wants to just verify real quick before it does anything, hey, please make sure your max width is not over this length. We just got to verify that. So that's what they do. They check the max length that you're about to do, and they make sure, like a sane person, just set the max width. It's a sanity check, right? Make sure you don't go over a certain width. Except when you compile it and then decompile it, it's an insanity check. What am I looking at here? This is bonkers, right? And this is all IDA Pro 9. This is the latest version. You can get your $8,000 license every year, right? This is crazy stuff, right? And we have these gotos everywhere. That's not so nice. The if statement has now nested inside of the other if statement. What's going on? We also have the same thing I showed you earlier, this like black magic. 2 calls have become 3 calls. This is some crazy stuff, right? So what is going on here? And I think a lot of you already know based on the title of the talk, right? There's some optimization stuff going on, some tomfoolery. But before we get to that, right, we kind of have to take a moment to stop and figure out how exactly do decompilers make this linear code that we're so familiar with. Right, so decompilers make linear code after doing a few other steps, right? You heard some awesome talks already about trying to get types back. This is associated with also getting variables, and you also have to get a control flow graph. And when you have all of those things, you have this control flow graph with variables, with some types, you have to turn the graph into linear code. And this is called control flow structuring. How does it work? Well, control flow structuring is, in the modern realm, in these modern decompilers, is about pattern matching. You know, those nice, the kid game where you try to put the block in the right thing, right? Square goes in the square, hopefully, ideally. So we have these different graphs and what we think they should look like in C. On the far left, right, this is probably a familiar structure to you, just a triangle. It's a conditional branch. You could take it, you could not. And then, you know, as we drift further on the right here, we have the classic if then else, a diamond. And then we have the switch statement, which is even more, you know, strict. You have to have a certain amount of nodes. You have to have a certain parents, ancestors, predecessors, all this stuff, different rules, different pattern matches. And as we get to more complicated things like loops, right? So generally what we do is we just take these graphs and we find them in the bigger control flow graph, a subgraph matching problem. So generally, this is how we do it. So here's a graph, right? A graph full of some nodes generated from some C code. We start at the bottom. Start at the bottom of this graph, and we try to match against it. So we take our kind of biggest C structure we know of, if then else here. We say, hey, try to match it. Make sure that the number of edges lines up. Make sure the conditions line up. Make sure the number of nodes line up. And it does, right? So that whole section is matched. You do not need to match it anymore, and we move up the graph. So we get to the second section up here. We have another structure that we hope matches, because this is the last conditional structure we have, i.e. the last structure we know of that could have two edges. And we try to match it, except we can't match it, because those two nodes have already been matched by the other thing. And that's a problem, because we're out of structures. There's no more C structures to define the graph that we're currently looking at. What are we going to do? So obviously, decompilers have figured out a way, or we wouldn't be decompiling right now. So what we do is we get rid of that edge. One of the two edges, you get to pick, do a coin toss. You get rid of the edge. It's called virtualization in control flow structuring. And you know, trust me, bro, it works. You remove it, it's not there anymore, and we all kind of close our eyes. We act like it's not there, and it's not there. So now we actually can match this. This thing matches to a structure called a sequence. It's just like you can imagine a line of calls is what a sequence is. And boom, we've now structured the entire graph. Just ignore that other, you know, the edge for a second. And boom, we get this great structured code, right? So you recognize the two if statements that we structured earlier. This is how we output this linear code now. And every single edge, every failure, every place that we could not figure out what C structure goes there becomes a go-to. And this is kind of the gist of this whole structuring thing I'm trying to say, is that every time you see a go-to in this decompiler, it's extremely likely that you're seeing a structuring failure. So you see 5 go-tos in your Ghidra output, that's 5 failures. There are 5 places where Ghidra likely failed to do any structuring correctly. And that's what you're seeing. So, you know, let's speculate for a second. Let's say you're not writing any go-tos in the code. We can write go-tos, normal people write go-tos, but for a second, let's consider there are no go-tos. So what happens then, right? How are we getting these unexpected patterns? How could you possibly compile code that had C structures, but then when you try to match it against C structures, they're not all there? And that's because, let's take the example of this switch statement, right? We expect to see this very specific thing, right? Structuring problems are much like relationship problems. It's mismatch expectations, man. It's just not working out here. Right? The switch, we thought it was beautiful. We expected this beautiful switch. It had a very nice set of predecessors, successors, right? We know all the things, except that's not what we got. We compiled this switch, and we got this messed up, right? We don't even understand all the edges. Who are the children of this graph, right? Like, I don't understand, right? I expected a switch, and what I got was this amalgamation. This is like modern control flow structuring catfishing, right? Unknown patterns. What's going on here? Right, so this is the problem, is that we are having these mismatches in what we believe is reality. So what is causing them, right? And that's the big kicker here, is these compiler optimizations, which I feel a lot of reverse engineers kind of intuitively know, right? Compiler optimizations are causing these weird mismatches. They convert what we knew as a normal switch statement into whatever the heck this thing is. And the biggest problem here is what people believe to be, is that this is almost black box. When something goes in, you can't possibly know what went in just looking at what came out, right? Seeing this amalgamation, you have no idea that it was a switch statement or if somebody actually coded it like that. But I am here today to tell you that there is a way, and there are methods to figuring it out. So there was something interesting about all the examples I showed you about optimization. And these aren't all optimizations we studied, but just some kind of interesting ones I wanted to show off. All of them have gotos. There's gotos in every single one. There's structuring failures in every single one. And that's quite interesting because these gotos are actually indicators that optimizations have run in a specific region of code. Look for the gotos, and that's likely where an optimization is. So how do we know that this is real? How do we know that this is something that stacks up? So we do a little study, right? We study a bunch of binaries. We use IDAPRO. We see, OK, all the way at the top of this graph, the top of the y-axis, this is when you have all optimizations on in O2. You'll notice there are 3,000 gotos. In the original source code, there was around 100. So we had a huge expansion of this, right? Nearly 30 times. If you go down just one bar on this y-axis, we disabled one optimization, the jump threading optimization. This one optimization got rid of nearly 900 gotos, or 900 structuring failures. And we continue this pattern all the way down to the bottom, disabling one optimization at a time. You'll notice that only 7 optimizations cause around 80% of all gotos and decompilers in these structuring failures, right? And more interestingly, of these 7, you can actually group them into 3 different types of kind of pseudo-optimizations or general optimizations based on what they do. For instance, jump threading is one. It causes code duplication. You know it happened because there is a goto and there is duplicated code. Another one is cross-jumping, which causes code merging. You know it's there because of a goto at the bottom of a graph. Another one is built-in inlining or switch lowering. This causes code movement. Right, so we can actually have a way to identify when an optimization ran. We have a pretty good way to say, hey, I believe this area had an optimization run in it. So the kind of gist here of these compiler optimizations that we just talked about is that you can actually find a lot of them. The compiler chain is not as lossy as we had thought it to believe. Even when you strip everything, you can't hide what's happening on the structuring level. So these gotos are indicators that these are actually happening. And not all optimizations are on the same level of destructiveness, right? There's just a few. I showed you just 7, and that accounted for nearly 80% of all failures, right? So these are things that if we remember correctly, we can de-optimize them. Because there's such a limited amount, why don't we just make a decompiler that de-optimizes each one individually? And we can, because we know how to find them, and we can study how they were optimized so we can reverse them. And now we finally get to plundering compiler optimizations. I wish I did the whole talk in this kind of pirate accent, but I don't have that confidence at this moment. All right, let's go back to the evil switch. The evil switch statement that is less evil than we originally thought it was. All right, so here's that switch statement. What happened? We compiled it, right? And it does look like this on the assembly. It is this flow down where we have all these nodes that run into each other. So IDA is actually being quite accurate about what it sees on the graph level. You'll notice, though, that each one of these nodes is doing a comparison on the integer level, right? These are all integers, all compared against the exact same register. And they're all following a specific pattern. So what this optimization is called switch lowering. It minimizes the number of jumps for a non-consecutive switch statement. You'll notice that those labels that were in the switch that we checked earlier, the cases, they were non-consecutive with each other. And so GCC tries to do some fancy optimizations to get a speed improvement. This optimization has existed since the early 2000s of GCC. It is quite an old optimization. They came up with it a really long time ago. Pretty good. And a kicker, you can actually not disable this optimization in GCC at all. It is non-disableable. It is on by default in O0. You can try and use developer commands. It doesn't work. You can then try to patch out the code. The rest of the code will crash because they have fundamental assumptions on switch lowering running. So the way you can identify this in runtime to figure out, OK, where did this switch lowering happen? You're looking for a graph with one variable that has integer comparisons that is in a very specific integer range. And the kicker of this is, of course, a goto. The goto tells you that this really is switch lowering. And indeed, that goto takes us to a default case of this switch statement. So if you wanted to do this in your own decompiler, right, this is the pattern you're looking for. Just do this pattern, search for this subgraph, and you find this goto. Another one, let's go to the mythical calls, the jump threading optimization that is responsible for making more calls than actually existed inside of the code, right? So if we compile down that code I showed you, this is what we get, right? A lot of stuff going on here. Pay attention to the bottom 2 arrows. We're going to these bottom 2 blocks. You'll notice that about, I don't know, maybe 60, 70% of these 2 blocks are exactly the same. These are almost exactly the same blocks. They just have a different ending, right? These are actually duplications of each other. So it is even duplicated at the assembly level. What's going on here is this optimization called jump threading. Here's a simplified version of that same code you saw, the one I showed you in the very beginning, right? So the important thing is these 2 if statements on the left-hand side, if A and B, and then a second if statement, if B. You'll notice that these have overlapping conditions. If you execute the first if statement, you will always execute the second if statement, right? And the compiler, of course, knows about this. It has good value set analysis and knows about these things. So it says, OK, if we're going to execute the first if statement, let's just always jump to the second one. You don't need to do another comparison. But wait a second, if we're about to jump, we need to copy every single thing between these 2 if statements. And so that's what they do. In this case, I only had a puts 2 between those 2 if statements. You can put much more code between the 2, and it will duplicate it as well. So that's exactly what's happening here in this one I showed you. You have max width option. It is checked to be not null first, and then checked to be null again. These are overlapping conditions. Jump threading hits, and boom, we get duplications. All right, so jump threading in general, this optimization on by default in O2, and it tries to minimize the number of conditional jumps, and it does that by duplication. This code duplication can be pretty aggressive. It's different per each compiler, but generally it's around 15 code statements that can be duplicated at any time. And these are C statements, right? Not instructions. So you can duplicate entire, like, if trees, the whole thing can get copied. I think in the worst case I've seen in real life has been like eight basic blocks have gotten duplicated across an if statement. And that's pretty confusing. Right, and if you wanted to implement this in your decompiler as well, you wanted to find the exact pattern I am mentioning, what you want to do, run one instance of structuring, you find the goto, do a search around the goto for this exact pattern. The pattern you're looking for is duplicated blocks. This middle block is going to have duplicated code. You need to check it on the IR level. If you're lucky, it will be just registers, but that's not always true. So you have to be a little bit smart about how you compare these. So is this all real? Right, like, am I up here just like hitting you with some theories, some crazy nonsense about optimizations and stuff like that? And the only way I can really show you that it is real is to just show you it's real, right? So let's do a quick demo. I don't know how many demos have run yet. Let's pray to the demo gods and show you a demo of our decompiler, which tries to implement these fixes. All right, let's show you the first one, just to give you a reminder of what the general structure of the code looks like. You don't need to read any lines again, but this is what normal format looks like in main. It's generally linear. It has a switch statement. It has the stuff that we mentioned in the talk earlier. Now let's go over to IDA. So now we go to IDA. Yeah, we have the crazy stuff. We have the broken switch statement I showed you. The ifs are gone. The labels are all over the place, right? The xdec2max has 3 instances, which is not correct. And you're thinking, binary ninja, my savior. Not quite. Same problems, different kind of effect though. Instead of having linear code with gotos everywhere, they actually moved most of the code inside this while loop. Now earlier in the code, only the switch statement was in the while loop, but now around 90% of main is inside the while loop, and it still has some gotos. And there's also the duplicated calls, right? So even our savior Binja may mess this up. Thank you, Binja, though. Ghidra, I'm not even going to go there. There's this Ghidra. And now we get to our decompiler. There's a dark mode, so don't panic, right? There's a dark mode. Don't worry. We're not Ghidra. There's dark mode. And we go to the code, and wait, oh no. No, I'm just kidding. Right? This is the switch statement. It got expanded into the ifs. But we have a cool feature here on the right-hand side. If you like to go crazy with levers, here is like 90 levers you can pull, just like a normal compiler, or you can use these 3 modes. Just like in normal compilers, right? You have -O0, O1, O2. In our decompiler, you have the exact same concept. You have basic, fast, and full, which are associated with O0, O1, and O2, different levels of deoptimization. So for this case, right, we have to go all the way to O2. We O2 it up, we hit apply, boom, and things start looking nice. Yeah, oh, thank you. Yeah, so the switch statement looks pretty good. We didn't get the characters right, but there's numbers there now. Right, so the switch statement has been placed in the correct place. It is inside the while loop, and it is the only thing inside the while loop. That has been structured correctly. The xdec2 max has been correctly deduplicated. There is no gotos here in this xdec2 region anymore. There's only 2 calls to xdec2 max, and this entire section is linear. You'll notice it's not nested in anything. It's in the correct place, right? And we have performed some other optimizations. There is a whole list of them here, a bunch of crazy stuff, but you can go and check them out if you want. Highly encourage you to see our decompiler, try it for yourself. You can test out these many different ways to hack around. The gist I kind of want to get at here is that this is fully customizable, right? You can do these different modes. You can mess with it. You can hack on it. It's open source. We encourage everybody to check it out. We love contributors. So let's get back to the main talk. All right, cool. So you guys got to see it work in this instance, right? And I showed you format, and I'm not just yapping about format. There's a bunch of different binaries you can test this on. We tested this on 26 Debian packages from the top 26 you can find. We tested it on some malware. But here's the results from the top 26. Basically, the important bars here is this yellow bar shows you how many gotos are there, how many failures. And this red bar shows you something called control flow graph edit distance. It's just a simplification of graph edit distance, so it's how similar is your code to source code. The important part is you cannot eliminate all gotos unilaterally. If you do, you get crazy difference from source code. You get those crazy nests that I showed you. But if you don't get rid of the gotos, you also have crazy broken things, right? Because they are structuring failures. So the key here is that you try to keep these failures low without deviating too far away from source code. And that's kind of these tests we did at scale to see how it works. In addition to that, there are more deoptimizations that I didn't get to talk about, specifically those 7, right? We did all 7 of them, and some other fun side bits of this that ended up in the paper if you want to check it out. We tested it against GCC, we tested it against Clang, MSVC, so all these different compilers to make sure these results still stay sane. We also had to run it against some malware. That worked out fine. Decent, right? It's still malware, still tries to break the decompiler, and these decompilers, if you haven't told from this talk, are still in their infancy overall across the board, right? And the algorithms are open source. If you're interested in any of this stuff, please check it out. There's some more code there you can see for all these open source implementations. So let's get to that final part, back to the goal. The original goal of the talk, the 2 realities that you as the audience get to choose from. How do you actually benefit from any of this nonsense I said about optimizations and decompilers and research, right? So there's really 2 options. You can take the first option, rebel, right? Get crazy, get in there, talk to all the decompiler developers you love. I hear they're in this room. And tell them that you need structuring APIs. You need a deeper way to mess with these decompilers, right? Things don't just stop at the IL. Things are more editable than we need to be able to edit everything. It's not just a stack of ILs. We need to be edit types. We need to be able to edit structuring. We need to be edit variables. All of this needs to be editable, right? And that makes a good decompiler. You can also demand of the people who fund these decompilers to do better. I hear they're also in this room. Demand better. Alternative, maybe you do some level rewriting. Finally, if you don't want to do any of those things, try the Anger decompiler, open source, hackable. There are limitations as there are with anything. Check it out for yourself. Thank you so much for listening. I hope you enjoyed it. Try our decompiler.
All right, we got time for one question. If there's one question you want to ask before we do a quick turnover, do we have it? Yes, in the middle. Here, grab it, Peter.
Yes, a question.
Testing. Did you do any testing on the order of deoptimizations? Because there's compilers, they do a lot of testing and tuning of the order of their optimization.
Yeah, so the order does matter, right? So we have a few deoptimizations that we have to try and flip like a few different ways in a fixed point manner until things stop changing. That format example I did, right, I didn't get to show you everything because in that case, we also had to undo constant propagation. You had to do that first, and then you had to undo jump threading. So the order does matter, and sometimes that can create, bad stuff. But if you have the right heuristics, you can kind of get around it. But yeah, it's a real thing. The order matters.
Excellent. All right, we'll go ahead and switch over to our next presenters.
you.
You can find Zion tonight at the event and talk over drinks and dinner about any other questions you have. So thanks again to Zion.
Thank you.